My talk, as he has already said, is on hazard ratio. Um, First of all, I must confess that I'm not a statistician. I'm a clinician, so I do not understand much of what I will speak today, but let me try to convey whatever little I understand. So to begin, of course, I think some introductory remarks are always in order. Good research begins by asking a good question, and publication, which of course is the end point for many of us, is the culmination of an idea. And a great publication germinates in a good idea often many years ago. And how do good questions occur? And I've listed some of the points there, but one very important input into getting good questions is meetings like this, when we get to meet physically with each other. And so therefore, it is extremely important to have these in-person meetings, and I'm delighted that this has started to happen again. So there are several concepts that are related to hazard ratio. Some of them are listed there, and to discuss only hazard ratio in isolation is a little bit difficult, but nevertheless, I thought I was given about half an hour. Let me see how much time I take. I will cursorily discuss some of these other concepts as I talk about hazard ratio. So we know the forms that data can take, and for the purpose of today, we are dealing with continuous data, and in particular time to event data, which is often called survival analysis. A very important, and I always try to convey this to the PhD students in ACTREC with whom I have the privilege of doing a class on survival analysis and statistics, that experimenters and investigators always use sample statistics as estimates of population parameters. And in terms of notation, population parameters are written in Greek letters and sample statistics are in Latin. So if you come across those, then you know that if it's a Latin, it refers to the sample, and if it is Greek, then it refers to the inference about the population. A sample is assumed to be representative of the population. It may not be the case. It may be the case to some extent, but not to the fullest extent. But nevertheless, that's the basic assumption of all statistics. I cannot perform a study on all patients with ER-positive breast cancer with whatever eligibility criteria. Therefore, I try to extrapolate, as Dr. Kumar and Amish were trying to do a little while ago, that from this sample of patients, I need to extrapolate to the patients that I treat in my clinic. So another just terminology, an observed value that is drawn from a sample is called a statistic, and the corresponding value in the population is called a parameter. And as I said, we analyze statistics and apply the results as parameters. Why do we need statistics? Each time we take a random sample from a population, we are likely to get a different set of individuals and calculate a different statistic. This is called sampling variability. And if we take a lot of samples from the population, the numbers that we get in terms of statistic will have often a predefined distribution about the true mean, which is 0.6 here. And in this instance, the distribution resembles a normal distribution. And I had initially thought I'll talk a little bit about the normal distribution because it is assumed to be the distribution in many of our analysis, but I will let that pass for today because of reasons of time. So the other thing that I just want to introduce very briefly is a point estimate, which is a single value, which can be a mean, a proportion, the difference between two proportions, and so on, and an interval estimation, which is a range of values, often called a confidence interval. And the reason this is important is because in hazard ratio also we talk about confidence intervals, and it often takes the form that is shown here. There's a point estimate, there is a interval to the left and an interval to the right, and that encompasses with some confidence the range of values that will be expected if you drew various samples from that population. And I will not get into the formula. This is, of course, I think many of you would know about it. The point estimate plus the standard normal deviate multiplied by the standard error of the mean, and very importantly, some common levels of confidence that we desire is a 90% confidence or a 95% confidence interval or a 99% confidence interval, and the corresponding alpha values are written there. And the Z value 1.96, you would have come across this term called 1.96, and this simply means that 95% of a sample of the values in the population are contained within plus 1.96 times the standard deviation and minus 1.96 times the standard deviation. And therefore, whenever we calculate at the alpha level of 0.05, we use 1.96. If I was to calculate at the alpha level of 0.01, I would use 2.58, and that would mean that's the third bell curve to your right, and that would mean that 2.58 times the standard deviation to the right and 2.58 times the standard deviation to the left will contain 99% of the values in that population. And this is essentially the meaning of the confidence interval. So the mean for a standard normal curve is assumed to be 0 with a standard deviation of 1. So how many times of the standard deviation is that value removed from the middle? And the farther removed it is from the middle, the stronger is the case for rejecting what we call the null hypothesis. So the confidence interval, of course, depends on the sample size. You have a smaller sample size, the wider the confidence interval. The inherent variability of that, whatever you are measuring in that population, and of course, with what level of confidence you desire to construct that interval with 95, 99, like I showed you earlier. And very importantly, when we compare two confidence intervals, we can compare them either by a difference or by a ratio. And when we do it by a difference, when you subtract one confidence interval from the other, it should not include 0. If it includes 0, that means that the null hypothesis cannot be rejected, and we cannot claim statistical significance. When it's a ratio, then it should not straddle 1. If it straddles 1, again the null hypothesis cannot be rejected. So let me now come to survival analysis, because that is directly applicable to the hazard ratio. In a broad sense, it involves data involving time to an event, and individuals enter the study at different times. They are followed up for variable periods and experience the event of interest, which could be death, relapse, etc., and so on, at variable time points in the study or not at all. And individuals who at the time of analysis of the study have not experienced the event of interest are said to be censored, and censoring can either be because you followed up the patient right to the time of your analysis but there has been no event, or somebody has not been followed up, lost to follow up without experiencing the event. And this is important. It is just shown here that these two individuals are censored, but they are to the left of the time of analysis. This individual is censored at the time of analysis because she or he has not yet experienced the event. So individuals enter and exit the study at different time points. Some exit with the event, some exit without the event. Now, one very important thing to note in many of these studies is the fact that the months on the x-axis is not calendar time. It's not January of 2021 and August of 2022. It is time from start of the study. So for each individual, the time starts at 0, and that's the time on the x-axis here. And although all of us know it, it's just good to remember this when one is thinking about these survival curves. So the underlying assumption of the survival analysis is that those who are not followed up for the entire period will experience the same survival experience as those who have followed up for the entire time. In other words, the patients are not dissimilar to each other, they are similar to each other. So if somebody was followed up only for 1 year and then after that we have lost contact, she would have experienced the same survival in the subsequent 1 year, which is experienced by somebody who's followed up for the second year as well. And that's a basic underlying assumption in survival analysis. And the other very important assumption, and I think this goes to the root of, on the heart of many of our retrospective analysis, the probability that an individual is censored should be unrelated to the probability that the individual suffers an event. In other words, censoring should not be informative. So in our retrospective analysis, commonly, if the bulk of the patients with whom we have lost contact are the ones who had somehow experienced the event and therefore did not come to the hospital, we would be overestimating our survival. And in many retrospective analysis where there is a substantial loss of contact with patients, the censoring is informative, which it should not be. So the other thing to think about in survival curves is that the Kaplan-Meier estimates are limited to the time interval within which the observations fall, and therefore it is incorrect to draw a line parallel to the x-axis beyond the largest observation and claim that that is a plateau. So, for example, in this particular study of cytoreductive surgery in ovarian cancer, we can only talk about survival analysis until the 84th month and not beyond that. We would not know what the survival experience of this cohort of patients would be. The other thing to consider here is that often, especially in metastatic situations, the median is achieved. And of course, it's a horizontal line that is drawn from 50% on the y-axis. But in many instances, such as here, and this is the SOLO-1 trial, the then analysis of the SOLO-1 trial, you can see that one or both of the arms would not reach the 50% mark, and therefore the median is undefined in this situation. And here, one often then talks about landmark survival as in 1 year, 2 year, 3 year, 5 year survival, etc. and so on. And that is why in many adjuvant situations, because the survival never, at least during the follow-up, never falls to 50%, you talk about 5-year survival rather than the median survival. So let me now come to hazard ratio, and there are two letters, there are two terms in that term, hazard and ratio. And hazard, because events are often defined in healthcare, are considered bad, and therefore the convention is to call it hazard. And ratio, this is the Oxford definition of a ratio, a quantitative relation between two amounts showing the number of times one value contains or is contained within the other. So essentially this means in simple English that there is a numerator, also called the dividend, divided by a denominator, also called the divisor, both having the same units. Therefore, the ratio has no units. So it is the numerator in some unit divided by denominator in the same units, and that's called a ratio. And the reason why I'm trying to just break it down is because we must understand what the hazard ratio is. So hazard ratio is a ratio of two hazard rates. So, for example, the hazard rate of smokers divided by the hazard rate of non-smokers. Now, I have introduced another term here called rate. First, I talked about a ratio. Now, I'm talking about the rate. Now, a rate is a special ratio in which the dividend and the divisor, the numerator and the denominator, are in different units. For example, onions at rupees 60 per kilogram. 60 is a unit of currency and kilogram is a unit of weight. Hardik Pandya at 120 kilometers per hour. 120 is distance and hour is time. So this is called a rate. So I told you hazard ratio is a ratio of two hazard rates. So hazard rate of smokers this is not strictly statistically, rigorously, mathematically correct, but it is approximately correct. Deaths per month, for example, and this is hazard rate 1. In non-smokers, hazard rate 2. And the hazard ratio is a ratio of hazard rate 1 divided by hazard rate 2, and therefore this is a ratio without any units. So this is the meaning of hazard ratio. In terms of hazard, so you will note here that the numerator is a rate and the denominator is a rate, and the ratio is the ratio between the two of them. Now, what is a hazard rate? Hazard rate is the probability that the event in question, if the event in question has not already occurred by the time that you are analyzing this particular patient, it will occur in the next time interval divided by the length of that time interval. And practically, the time interval is made very short so that in effect, the hazard rate represents almost an instantaneous rate. And mathematically, it is listed, it is written there, limit delta t to 0, the probability that an event will occur in the next instant in this patient if it has not already occurred by now. And as you can see, the hazard rate, it will always be positive and its limit is up to infinity. And the hazard rate, the unit of the rate is probability per unit time, probability of the event per unit time. As I said, it is always positive, has no upper bound. Now you can see here, this is not a survival curve, it is derived from a survival curve. The horizontal line at lambda in the upper cartoon is essentially a hazard rate that is constant over time, and this is called the exponential model. And the reason why this is important is that almost all, barring very few of our analysis, assume the exponential model to be true in survival analysis. But at the bottom, you can see that the hazard rate need not necessarily be constant over time. It can increase, it can decrease, it can assume various shapes. In the bottom right, the one on the top is called the positive variable and the one at the bottom is called the negative variable. So I have introduced a concept called hazard and we know something called survival. So in some sense, they are the converse of each other. So you can derive the hazard from survival and you can derive the survival from hazard. And I will not sort of explain these formulae, but on the top is a survivor function, which is an exponent of the negative integral of the hazard. So that's integral calculus. And on the bottom, hazard is a derivative of the survival, which means differential calculus. So on the top is the integral calculus, at the bottom is the differential calculus, and that's how you derive one from each other. And they are in a sense the converse of each other. If you know one, you can know the other. Now, very briefly, when we have two survival curves, one of the common tests that is applied to determine whether one differs significantly from the other is called the log rank test. And this is nothing but a variation of the chi-square test that we all know about for comparing proportions. And essentially, it compares the observed number of events versus the expected number of events at each point of time. Very similar to the very controversial WHO estimate of India's COVID deaths observed versus expected, but at each point of time on the curve. So how do you compare two hazard rates to arrive at a hazard ratio? In this example, you have these two survival curves here. There is a delta in survival that I have just shown. You have the survival curve 1 with its corresponding hazard rate 1, and I'm assuming that there is an exponential model, so the hazard rate is constant. You have the survival curve 2, and you have its corresponding hazard rate 2, and the ratio of these two hazards is called the hazard ratio. Now you will note that the survival curve with a lesser survival has a hazard rate that is higher than the other one. So like I said, they are the converse of each other. The blue lines, the blue survival curve is below the red survival curve, but the blue hazard rate is above the red survival, the red hazard rate. And that's how you statistically, mathematically derive the hazard rates. And mathematically, the hazard ratio is the hazard rate of the arm 1 divided by hazard rate of the arm 2. So let me now just very briefly in the next 10 to 15 minutes illustrate some practical points about hazard ratio, and as far as possible I will take my own papers which I have analyzed or I have contributed to significantly. So like I said, Amish just mentioned that the hazard rate was something in the first 6 months, then it became something else in the next 8 months, and so on. So on the left, the cartoon here shows that the ratio, and now this line is not a rate, it's a ratio, it's constant over time. This is called proportional hazards over time, and this is the basic fundamental principle of the Cox proportional hazards analysis, which all of us know about. If there is any violation of this constant hazard ratio, then we must do one of the 3 or 4 or 5 things that need to be done. And on your right, you can see on the left was a ratio. Now these are the actual hazard rates of the two arms, and you see that they do not remain proportional over time. They are not parallel to each other over time. They cross. This is an extreme example of non-proportionality, but there are less than extreme examples where they don't cross, but they either converge or they diverge significantly from each other such that the hazards are not proportional. So let me show you a recent example of how we use this. We published this paper in the International Journal of Infectious Diseases. This is the incidence of SARS-CoV-2 infection in the employee cohort of Actrec through the second wave of the pandemic in India and the effect of prior infection and vaccination on this rate. So first of all, we wanted to look at the incidence of SARS-CoV-2 infection before anybody had received vaccination, and this is a univariable analysis. And we wanted to find out whether males and females differed from each other and whether older and younger individuals differed from each other. Now you can see this is survival, but this is 1 minus survival. So this is going from bottom to up rather than a survival from up to down. And this is the same. This is just 1 minus survival because I want to show the cumulative incidence of COVID infection. Now you see in males and females on the left, there is no significant difference. The 22.7 versus 21.9, P is 0.32. And on the right, in older individuals also, there is hardly any difference. The percentages are the same and the p-value is the same. But if you look more closely at this survival curve, or rather 1 minus survival curve, you notice 2 periods, the very initial period and at the end, where the 2 survival curves come close to each other for gender and also for age. But right in the middle, there is a separation of the curves. That means that by inspection of this survival curve, I can make out that the hazards are not proportional over time. There may be some time period when the rates of COVID infection may differ between males and females and between older and younger individuals, although averaged out over the entire period that I analyze this data, this may not be the case. So what did I do? I thought this is not proportional, so I checked the proportionality assumption by entering what I call an interaction term of sex by time and age by time in the Cox model. Now what I did was this. So you can see here that I entered in the Cox model sex, age, and then 2 terms, sex by time and age by time. And now you look at the p-values, the 2 interaction terms are statistically significant, and actually age and sex both become significant. And therefore, after adjusting for the non-proportionality of hazards over time and the interaction between gender and the propensity to get COVID infection over time, actually now female sex and younger age were both associated with significantly lower infection compared to the other categories. But please note that statistical analysis can only confirm that the hazards are not proportional over time, and I have adjusted for that, I have corrected for that. It cannot tell you what is the reason for non-proportionality. That has to come from outside statistics. I have to think why, females should have a lesser infection in this time period, but not in this time period and in this time period. That is not statistics. Statistics will just confirm whether there is non-proportionality, but the reason for that non-proportionality and the differential hazard ratio has to come from domain knowledge and other insights which Amish often has. So another very important point about hazard ratio is about subgroup analysis and interaction. Now this is the Solo 1 trial. And you can see right on top in all such forest plots is all patients, or right at the bottom. And these are all the subgroups with various categories defined. Now let me show you what is the meaning of subgroup analysis and its interaction analysis. Now this is the benefit or not of olaparib versus placebo by BRCA1 or BRCA2 or their combination status. And you can see that for BRCA1, olaparib versus placebo has a hazard ratio of 0.4, whereas for BRCA2, olaparib has a hazard ratio of 0.2. Now the question is olaparib more effective in patients with BRCA2 compared with patients with BRCA1 mutation? And if I was to put that in statistical terms, is a hazard ratio of 0.2 for olaparib versus placebo in BRCA2 significantly different from a hazard ratio of 0.4 for olaparib versus placebo in BRCA1? Remember that because of the sampling, because we are not studying the entire population, no two quantities can directly be said to be more or less compared to each other. We have to always compare them with a test of significance. So although 0.2 is less than 0.4, but in statistics, 0.2 may not be less than 0.4. So that's so the comparison of the two hazard ratios within those two subgroups defined by that variable is what is called the test of interaction. And the point that I'm trying to make is, unless significantly different by a test of interaction, the effect of study intervention cannot definitely be said to be different within the two subgroups. Again, some examples from our own studies. This is the study that was performed by Dr. Badwe, preoperative progesterone in patients with operable breast cancer. And you see that for all patients, there was no significant difference between DFS on the top and OS on the bottom. But in patients who had node-positive disease, there was a significant difference, a betterment with progesterone, a benefit of progesterone both for disease-free and for overall survival. So when we looked at the forest plot here, these are the subgroups defined by nodal status. And you see that for node negative, the hazard ratio of progesterone versus not is to the right of 1. And for node positive, it is to the left of 1. This is for disease-free survival, and for overall survival, it is exactly the same. So what we did was, we did an interaction analysis, and I will just tell you how we did that interaction analysis. And you see, I have highlighted the nodal status on both those interactions, and both of them are statistically significant. That means that the hazard ratio within node negative is significantly different from the hazard ratio between within node positive patients for progesterone versus not. And the clinical meaning of this is that there seems to be a benefit of progesterone in patients with node positive disease, but actually there seems to be a detriment of progesterone in patients with node negative disease. So this is another example of our own study. This is the neoadjuvant chemotherapy surgery versus CTRT in CA cervix. And for the entire cohort, we showed that CTRT was better than neoadjuvant chemotherapy, and this was statistically significant in terms of disease-free survival. But if you look at the various stages, on the top are stages 1B, 2 and 2A, there is no difference between CTRT and neoadjuvant chemotherapy followed by surgery, but within stage 2B, you can see that there is a marked betterment with CTRT compared with neoadjuvant and surgery. And again, when we did the interaction analysis, we found that there is, so that P is 0.04 for the interaction between stage and CTRT versus NACT, that is statistically significant. This means that for some reason, neoadjuvant chemotherapy and surgery results in equivalent outcomes in patients with stage 1B2 and 2A disease, but CTRT is significantly superior to neoadjuvant in other patients. But for the other subgroups, there is no significant interaction. Now, the first example of progesterone is what is called a qualitative interaction, and the second that I showed you for cervix cancer is actually a quantitative interaction. A qualitative is when the results seem to be opposite in the two groups. In a quantitative interaction, the magnitude of the benefit is different, but it is in the same direction. But in both examples, there was a significant interaction. And operationally, again, as with the proportional hazards, how this was tested, we entered a term called progesterone yes versus no by nodal status positive or negative in the Cox model, along with the other covariates. And in the cervix cancer trial, we entered an interaction term called treatment, CTRT or NACT surgery, by stage, 1B2, 2A or 2B in the Cox model, and then adjusted for it, and then found that those terms were significant. Again, let me say that please note that the statistical analysis can only confirm that there is a significant interaction between a study treatment and a variable, but the reasons for that interaction are non-statistical. That we have to get by our own insights as to how and why that might be happening. So I think there was a bell. Shall I stop? I think, okay, so let me stop. I had a few more things to talk about in terms of the types of comparison, superiority, equivalence, and non-inferiority. So let me, skip this. I think many of you know about this. I had wanted to give you some examples. Please continue. Should I? Yes, please. Okay. Start from where you had stopped. Okay. So the third point, practical point about hazard ratio that I wanted to say was the types of comparison, which is superiority, equivalence, or non-inferiority. And superiority is when the point estimate and its two bounds of its confidence interval are either entirely to the left or entirely to the right of one. That is superiority. Non-inferiority means that the right bound, only the right bound of the confidence interval is entirely to the left of a predefined non-inferiority margin. And I think Kumar was discussing about, non-inferiority margin with a hazard ratio of up to 1.5, 1.8 or 2. But in this instance, the non-inferiority margin is the positive bar, and you can see that in the upper two confidence intervals, the right bound of the CI is entirely to the left of the non-inferiority margin. In equivalence, both bounds of the confidence interval have to be entirely within the left and the right boundary of the equivalence margin. And this is the fundamental way in which we think about superiority, non-inferiority, and equivalence. Now, again, one of our own studies. To illustrate this, you all know that we did a meta-analysis of shorter durations of trastuzumab versus 1 year, and this was an individual patient data meta-analysis based on extracted data, and we claimed that there was non-inferiority. But what actually happened? So this is the actual forest plot, and you can see that we set the non-inferiority margin at 1.3. Why did we do that? For those 6 trials, there were different non-inferiority margins, and the median was 1.3. So we chose the median of those six trials. Now you can see here that the hazard ratio for less than 1 year versus 1 year of trastuzumab is 1.14 with a 95% CI of 1.03 to 1.25. Now if you see the right bound, which is 1.25, is entirely to the left of 1.3. So therefore we claimed non-inferiority. But somebody can also say that the left bound is entirely to the right of 1, and so therefore they can also claim superiority. So this is superiority of 1 year versus less than 1 year. So the point that I'm trying to illustrate here is that sometimes the reasoning has to be extra statistical, it has to be non-statistical. What you want to know is that, okay, less than 1 year can never be better than 1 year, but how much non-inferiority can we accept? This is an example where both non-inferiority as well as superiority can be claimed from this particular analysis. So non-inferiority of less than 1 year versus 1 year, and superiority of 1 year versus less than 1 year. So the last practical point that I want to make is about relative versus absolute benefit. And Dr. Penston wrote in the BMJ more than 10 years ago, and he wrote very colorfully. Surely enough has been written over the past 20 years to show that the use of relative risk reductions is nothing but a deception. Yet this misleading measure of efficacy continues to sully the pages of medical journals. Many of us may not agree with the extreme language that is used here, and he goes on, researchers and their sponsors know that selling their wares on the basis of trivial absolute differences between the study groups is an uphill struggle. and instead resort to presenting the data in terms of relative risk reductions. This state of affairs should not be allowed to continue, and he goes on to, state it rather colorfully. I suggest that you read this. This is a short letter. So I had used this with Amish when we did the oncology beyond the obvious. You can see that these are two hazard rates for this study shown here, and the relative risk reduction by the study treatment is 19% with a p-value of 0.045, and this is of course the affinity trial. The absolute benefit was 0.9%, and you can see that there is hardly any distance between the survival curves. This is at least as of the first analysis. So the point that I'm trying to make is, and this is the Monarch E trial, I just wanted to show you that the absolute difference in DFS at 2 years is 3.5%. That is depicted by A, that small arrow A there between the two arms. But if you see the hazard ratio, it is 0.72, which is a 28% reduction in the risk of death or relapse. Now, how is this derived? So what I'm going to show you is a mathematical approximation. It is not the exact formula, that is more mathematically complex, but this is a fairly good approximation. So the event rate in the control arm, and now I've drawn a big arrow B from the control arm right up to the 100% point, and that is 11.3%. So the relative risk reduction is essentially asking a question, what proportion of B is A? How much of B is A? So A is 3.5%, and that 3.5% is out of a total possible relapse rate of about 11.3%. So 3.5% of 11.3% is 30%. And this is fairly close to if you calculate it by the hazard ratio, which is 28%. So this is the meaning of relative risk reduction. So here the relative risk, so about 1/3 of the 11.3% events were reduced by abemaciclib, but abemaciclib improved in absolute about 3.5%. So that's the meaning of relative and absolute. And there are a few things about the hazard ratio and event proportion. So how is this determined? So if you just think about it in your mind, a modest hazard ratio in a population with poor outcome in the control arm will lead to a large absolute benefit, but a strong hazard ratio in a population with excellent outcome in the control arm will lead to a smaller absolute benefit. And if you see, a strong hazard ratio in a poor outcome population is hitting the bullseye, and a weak modest hazard ratio in an excellent outcome population is a dud. So there are those four possibilities about how hazard ratio and the prognosis in the control arm interact with each other to produce the absolute survival benefits. I've given you an example here. Suppose the 5-year disease-free survival in the control arm is 30%, so therefore the event rate is 70%, and if the hazard ratio is 0.87, there's a 13% reduction in events. Now what is 13% of 70%? It is 9.1%. But if you see a second situation where the 5-year disease-free survival in the control arm is 92%, so therefore the event rate is 8%, and now I am gaining a much stronger hazard ratio of 0.6, which is a 40% reduction in events, but the absolute benefit is 40% of 8%, which is 3.2%. So, of course, it is correct to say that there is a 40% reduction in the risk of death and relapse, etc., and so on. But it is also true that 3.2% is the actual benefit of whatever you are planning to do. So the reason why absolute benefit is important is that it is the actual number of patients out of every 100 that you treat with the new drug or the new treatment who will benefit from it. If you treat 100 patients, 3.2 are likely to benefit from it, not 40% as in the relative benefit. And this is the last thing, and I do want to quote, this is Stephen Jay Gould. He's a known philosopher. Some of you have read it. Many of us like him. He was diagnosed with peritoneal mesothelioma in 1982 with a predicted median survival of 8 months. And he wrote this many years later. The median is in the message. And I will quote from him. I immediately recognized that the distribution of variation about the 8-month median would almost surely be what statisticians call right skewed. After all, the left of the distribution contains an irrevocable lower boundary of zero, but the upper half can extend out for years and years. The distribution was indeed, he searched the Harvard library and he found that the distribution was indeed strongly right skewed with a long tail, however small, that extended for several years above the 8-month median. I saw no reason why I shouldn't be in that small tail. And so the median is not the only value. Both doctors and patients get stuck onto the median or the mean. And in the recent times, of course, the tail of the curve has gained increasing attention for a variety of reasons. But nevertheless, this is direct, the words of Stephen Jay Gould. And by the way, after 1982 with a peritoneal mesothelioma, he eventually died in 2001, and he lived for 20 years. So thank you very much for your attention. And there was this time when this was for ₹3. Thank you.
Thank you, sir.
Yeah, thank you very much.
Yeah, I'm sure, sir, the student will benefit from this talk and they will be wiser in interpreting the studies and maybe planning someday. Sir, I don't see any question in the chat box. And to start with, I'd like to ask you one question, sir.
Yeah.
So you showed us. You showed us how to interpret the hazard ratio in a subgroup analysis. But sir, many times we are faced with a situation where we are forced to compare the hazard ratio across the trial. For example, I will give you one practical example, sir. In myeloma setting, in the relapse setting, daratumab is commonly used drug, but the best partner with this drug is not known. And there are 3 trials where it is combined with IMID, it is combined with proteasome inhibitor, and sometimes it is combined with another kind of drug. And people try to look at the hazard ratio within the daratumab across all these things. So, sir, can you talk on this a bit, how to interpret and how to go about it?
So it is very difficult to strictly compare the hazard ratios across trials. And of course, the fundamental reason is again sampling variability. The eligibility criteria for various trials are different, even though they may have similar kind of patients. The baseline prognostic factors are different. And so therefore, it is difficult to really ascribe a difference in the hazard ratio to a difference in the 2 treatments compared to the contribution of the prognostic factors themselves. So with that caveat, I think one has to try to game in one's mind how similar are the 2 populations in the 2 trials, and then having thought about that for a moment, one has to see whether a hazard ratio of treatment B versus treatment A in trial 1 of 0.6 is different from the hazard ratio of treatment C versus treatment A in the next trial, and that hazard ratio is, let's say, 0.87. So how different is 0.87 from 0.6? We have to take into account all the variability of the patient characteristics, etc. I would also like to add that in the example that I just gave, I assumed that the control arm is the same in both the trials. But it is also the case that even the control arm may have some variation between trials. So there is no strict statistical way of comparing hazard ratios of individual trials across trials. But of course, all of us know that when we perform a meta-analysis is a kind of a compromise where we say that we will accept patients of one kind across all trials, and even though that one kind may have some variation, we'll tolerate that variation. And so therefore, one way of comparing across different trials is to perform meta-analysis, collect similar patients versus similar patients across trials and then compare them. The other way to do that is what is called a network meta-analysis,
or a network analysis where, you know, A is compared to B in one trial, B is compared to C in the other trial, and C is compared to D in the other trial. So therefore, by extrapolation, you can compare C to A. But let me say that meta-analysis as well as network analysis as well as simple comparison of hazard ratios across trials is done, but they can only be pointers. They should not be taken to be the definitive answer on whatever question one is wanting to ask.
Yes, sir, yeah. Thank you, sir. That is good. If anyone has any question, they can unmute themselves and ask.
बाहर click करो so that So Lingaraj has a question. So you discussed about informative censoring. How to evaluate whether there is differential informative censoring. So one way to do that is that in all statistical software, you can plot a visual representation of the censoring that has happened in the two arms of the study. And it will give you each patient who's censored will represent a dot, and on the x-axis is the time, and you can compare the proportion of patients visually as well as quantitatively as they are censored over time. And that should approximately be similar across the two arms, and that is one semi-quantitative way of thinking about whether censoring is different. But this essentially tells us whether in one arm many patients are censored early in the course of their treatment and in the other arm they are censored late. That may be so that is one type of unequal censoring between the two arms. But qualitative censoring essentially means that the patients who are censored are different from the patients who are not censored and who are followed up right to the end. And there is no statistical way of doing it except to figure out non-statistically whether there may be some reason why censored patients may be different. So for example, a common fallacy in overall survival analysis that are retrospective is that patients, when they are end stage, they are sent back home, and you know, it is said that now nothing more can be done, and eventually their deaths are not recorded. And there are other fewer patients in that analysis who actually die within the hospital. And the patients, of course, the good prognostic patients are followed up right till the end and they don't die. So, you know, if you censor all the bad prognostic patients, not bad prognostic, all the patients who had terminal stage disease and who were sent back home, and if that is counted as a censoring in your analysis, then that is informative censoring. Because the reason is that you sent back patients who are likely to have died very soon after you send them back home, but you have not actually recorded the act of death. Compared to patients who are not censored, they are the good prognostic patients, you have followed them up right to the end. So one has to think non-statistically for about any reasons why patients who are lost to follow up or who are censored may be systematically different from the ones who are not censored. So I explained two things. One is the difference. We have to think whether there is any difference between patients who are censored and those who are not censored. And the second is to plot a visual plot of the censoring in two arms of the study in a randomized trial or in any other comparative trial, and to see whether the pattern of censoring early versus late and the actual proportions is different between the two arms. So I'm not sure if I answered your question, but that's how I think about it.
Thank you, sir. I don't see any questions here. If anyone has any question, they can unmute themselves.
There is one more in the chat box. Yeah, so, okay. Okay, so if there are no more questions, then...
Sir, last 1 minute, sir. So, sir, all our students are hearing it right now. And what do you think, how do they should approach their statistical studies, sir? Any tips for them, sir?
So that's a very difficult question. I'm often asked that question. Actually, there is no simple way of explaining what to do. So I can only tell you this, that, you know, although teachers and whoever gives you the lecture or whoever explains can give some pointers and show some kind of a path, but the actual learning and the understanding of the subjects happens by doing it yourself. So there are a number of relatively simpler books on statistics, and the only way to do it is to read it. And believe me, mathematical reasoning, statistical reasoning, probabilistic reasoning is not easy for anyone. So, it is not like a factual information about heart failure where you just read it and the fact is the fact. Here, there is some bit of derivation, some bit of deduction, as well as deductive as well as inductive reasoning. So one has to go back again and again to try to understand it. And it's a slow and painstaking process. And if one has the affinity for doing it, then one will do it. So that's how it is. There are a number of nice lectures on the YouTube. There are a number of books, there are tutorials, etc., and so on. But all of that will require some bit of active mental engagement by whoever is wanting to learn. So that's all that I can say.
Yes, I think that's important point, sir. So thank you for that. And I really like to thank you. Our scheduled lecture got postponed and you stepped in last moment to cover for this lecture. So thank you, and we'll end class here.
Thank you very much.